Let's zoom that out a little bit. Okay. All right. There are the odd minus signs here and there remaining, but yeah, you can see that comes from that curl. Okay. Okay. So where did we get to? So we've had a little merry journey, looking at a number of different relations between the electric and magnetic field for a plane electromagnetic wave. And where we got to last Friday was to look at the energy content of a moving plane wave. Okay? And where we got to was this statement, which was the energy density. Let's put that there. The energy density of the electric and magnetic fields. Let's zoom that in a little bit and make it a little clearer. Okay. So we had the energy density in a plane wave, and we saw the following facts. Firstly, the electric field part. Is that bright enough? Seems okay. Is that clear enough? Yeah. I think you can see it. The electric field clearly has an electric field component, and it has a positive definite magnitude because of the square when I find the energy density. And we had the same type of expression for the magnetic field energy density, and then of course you see this factor 2 that appears, and then you wanted to confirm that the electric and magnetic field energies were equal, which is straightforward to do because you know the relationship between B0 and E0. Okay, that's easy enough to do. And we could say there was the same energy in the electric and magnetic field. Okay, so therefore we can write that down, we can sum up those two parts, and we can look at the electric field component, and we simply take away that factor half. Right? So factor 2 has disappeared, or factor half has disappeared. Right? Okay, and we could see by drawing out what the energy looked like as a function of position. So this is the propagation direction Z of the wave, and we're taking a snapshot at some fixed instant. We see the wavelength of the wave manifesting itself as the distance between two maxima of the energy densities. And conversely, if we look at a fixed Z position, imagining the wave propagating over it, the energy density rises and falls. So quite straightforwardly you can see that there must be energy moving from place to place. Each one of these lumps is moving along. Okay? Right, now, we can now calculate, this is the next step, that we can now calculate the time average of that total energy density U, and we can calculate it as follows. All right? The time average of U is simply equal to epsilon naught E naught squared, and I take the time average of cos squared, and hey presto, a factor of half appears again. So watch out for those two factors appearing and disappearing. Okay? They're very easy to drop and add in by accident. Right? So the time average of the energy density is equal to half epsilon naught E naught squared, where E naught is the peak electric field over time. Okay, so it's the maximum value of the electric field you see at any particular time, and we'll see this all the time when we look at waveguides later. So watch out for that factor half. Okay, we can also express it in another way. Rather than expressing the time average of the full energy density in terms of the peak electric field, we can also express it simply epsilon naught times the RMS electric field. So again, there's another factor of 2 that appears. Okay? And remember, we define the RMS electric field as being 1 over square root times the peak electric field. Okay? So this is about, 0.86 or so times the peak value, okay? Which you've seen a zillion times before. All right. So that's the energy density. So we have seen, therefore, that if I have an electromagnetic wave, there must be energy moving from place to place. But we've already seen that, haven't we? We've seen that in the context of defining this thing called the Poynting vector, which is what we'll go and talk about now. Okay? So we're going to relate those two facts now. But before we do that, let's just remind ourselves what we mean by energy flux. Okay, so let's remind ourselves what the units are. So energy flux means I have a certain amount of energy density per unit volume, and it is moving at some velocity, given in meters per second in SI units, of course. So therefore, that is in joules per meter squared per second. So you can see it's a certain amount of energy, or a certain amount of power, that's joules per second, passing across a given unit area. Right? Okay, now, we saw that previously when we defined this thing called the Poynting vector. Right? Remember, with a y. I love those weird accidents of history, pointing being the direction it goes, but that's quite... Anyway, that's me, I suppose. You may not find it quite as interesting, but there we go. Maybe we'll later. Okay, so here's the Poynting vector S, and remember we defined that. That was telling me the direction in which energy was being carried, and we saw that in an earlier section where we were talking about... let me just show that part. There we go. We defined the Poynting vector by means of this energy balance equation, didn't we? Right? So we said here's a volume, and we had a rate of change in time of the electric and magnetic fields, and then for that given volume, S was telling me what must be either leaving or entering that volume through those surfaces, S. Okay, so that must be S must give me the direction in which the energy is flowing. Plus, there was this work done on the charges. So there's another bit where work is being done by the charges, and that work can only be done by the electric field. There's no magnetic field there, right? Okay, and remember we defined S as being this Poynting vector value. So whenever I had an electromagnetic field, I can find my place again, there we go, that was equal to 1 over mu naught times E cross B. And everything pointed the right way, didn't it? Because in our plane wave situation, E was perpendicular to B, and S is perpendicular to both of them. So, now we look back at our plane wave solution. So in our plane wave solution, in this case, S explicitly is equal to 1 over mu naught. Well, the dot product just becomes a multiplication, and the direction is simply given by Z hat. Okay? And that's for the electric field. That's a very poorly written B. There we are. That electric field and magnetic field are both varying in time. So really I should be writing it down as 1 over mu naught, some peak values of the electric magnetic field, and then my time varying bit, which of course we're going to average out in a second. Okay? And then I just write down the direction if I care about the direction. Okay? Right? So we just note here that Z hat is the direction of propagation, and we've seen now propagation. We've seen in several guises that the direction of propagation is also the direction of the energy flow. So those concepts are coming together now. So now we just do the same thing we did before with explicitly with the energy densities. We can average over time. So at any given location, at a given instant of time, the Poynting vector is rising and falling along with the magnitude of the electric and magnetic fields. Okay? And remember, the electric and magnetic fields are coupled together. They go up and down in phase with each other. Right? So if we observe at some particular plane, the S value is going up and down, but it has a time averaged value, and that time averaged value, denoted by these little brackets, is 1 over mu naught E0 B0 times a half again. Okay? Right. Because I'm getting more enthusiastic now because this is the more fun bit, isn't it? We've done all the turgid bit looking at plane waves, which you've seen before. This is new, I hope, and it's quite fun. Right. What can we do with that equation? Well, let's rewrite it a little bit, because we can straight away rewrite it in terms of the electric field only. So let's do that. We put our c squareds in, epsilon naught mu naught, E naught squared, okay? And let's rearrange that by moving those mu naughts and E naughts around, and I can write that as 1 over root epsilon naught mu naught times half epsilon naught E naught squared. Why would I want to do such a thing? Because I can observe two quantities, and these quantities will be different later. Remember, this is in free space, clearly we can identify this part as being the time averaged energy density. Okay? And this bit is how fast it's moving. Okay? So we can relate the time average of the Poynting vector to the time average of the energy density, and it's telling me that S equals CU. Okay? Cool. So we can relate the energy density, whatever the energy density is, the energy density of the given volume, well, clearly it must be moving at the speed of light in the vacuum, and that tells me how much energy is moving from place to place. Sort of obvious, isn't it? Right? Later on we'll see that the energy densities and the speeds are modified in different situations, and in particular waveguides are kind of funky for that reason. All right, now, electromagnetic waves are made of photons, aren't they? And we said right at the beginning that we were going to avoid mentioning photons at all costs because this is a classical course. However, sometimes we have to do it. And one of the areas is in the concept of radiation pressure. So we should talk about radiation pressure. And this is the last thing we're going to talk about until we move, and then we'll move on to looking at how radiation is generated, which is, of course, the big reveal, right? So, radiation pressure. So we've seen that energy flows in a plane EM wave, and when we generate it by some means, so we might have like a TV transmitter or a radio transmitter. Okay, so if you look out from the 6th floor, you can see on that big hill to the northeast-ish, you can see Winter Hill. There's a radio transmitter, and it is giving you energy that's emanating from it, and that wave, as it propagates away, is going to reduce in energy flux by some value 1 over r squared, however far away you are. The total amount of energy per unit time emitted is approximately a constant, isn't it? And the further away, the fewer the photons you have, and presumably that means the less pressure that those photons will carry. Okay? But this is also true for all these other things. Right? You have mobile phones, which is the same basic principle, but at lower power. You may wonder, if you have a microwave oven, there is electromagnetic energy, there are photons inside that oven, they're bouncing around, and I encourage you now to have a look online. There is like a description of how the microwave oven works. It'll become a bit clearer later on when we talk about cavities and waveguides. But microwave ovens have those photons inside them by virtue of there being electromagnetic energy generated in some manner. And those photons are bouncing off the conducting surfaces, and therefore they should also be pressing on the walls. Which does lead you to think, doesn't it, that if I had a microwave oven and I launched it into space and I plugged it into a big battery and I opened the door, sure, that means photons will come out the door end, assuming I've overridden the circuit. There should be a door lock in it, right, that turns it off. Let's say I override that. There's some YouTube videos on that, but I don't encourage you to copy them, right? So you open the doors and the photons will come out the door, which should mean that the microwave oven goes the other way. It turns into a rocket, doesn't it? It should do, and that's true. Okay, you can calculate how that works, and we might do that later. Okay, all right. And in fact, there are, I hesitate to call them death rays. We try not to talk about such things, but people do talk about energy-directed weapons, and they're basically apparatuses or instruments that create electromagnetic radiation, which is directed in some manner. We imagine it will spread out. Okay, which we'll talk about later, but those are basically extensions of these ideas. Okay, and in all these cases, the electromagnetic waves are carrying momentum. Okay, now this is where we have to use our quantum picture, right? It may or may not be possible to easily derive that an electromagnetic plane wave transfers momentum as it propagates. It's much easier to do it with photons. Okay. So we're going to consider our EM wave. Right, so consider our EM wave equivalently. I used to have such lovely handwriting when I was an undergrad. As a fluence of photons, where fluence is slightly different from flux. Fluence is a counting value. Okay. These terms are often used slightly interchangeably, but we'll use fluence for counting certain numbers of photons which are all of the same kind. Okay. Now, obviously, we already know that E squared equals P squared C squared plus M naught squared C to the fourth. That's our general relativistic formula, right? And we know for photons, m0 is 0, obviously, right? And therefore, if I have a certain amount of energy in a set of photons, I have a certain amount of momentum p, and p is equal to E over c, irrespective of the wavelength. That's an important thing to realise, isn't it? So therefore, if I have an energy density, which we've just been talking about, there should also be a corresponding momentum density, which is the energy density divided by c. Okay? So let's calculate that momentum density. Because that will then work, if that momentum density is now moving in the same manner that the energy density is moving, that's our Poynting vector statement, we should be able to work out what the radiation pressure is. Now, we need to be a little bit careful about defining our symbols. Okay? So I'm going to call the momentum density P subscript A, just to distinguish it. Okay? So that is the amount of momentum, kilogram meter per second, okay, in a given volume per meter cubed. So therefore it has units of kilograms per meter squared per second. Okay? Right. So if I have a certain energy density, remember we're talking about a time average quantity here to just keep things simple, right? I can relate the magnitude of the momentum density to the magnitude of the energy density. It's clearly just divided by c. Right? That's easy enough. And obviously we already know what the Poynting vector is. So we can now relate the momentum density of the electric and magnetic fields. So that is equal to S over c squared. Okay? So remember what we're doing here is we're saying, here's some volume which contains this U and this momentum density and the electric and magnetic fields and the Poynting vector. And we're now thinking of it, remember the wavelength doesn't matter, but we are realizing that these this EM wave is really carried by photons, and they're going to, as they travel out one end of that volume, moving at the speed of light, they're going to exert a pressure on some surface. That's what we're calculating. Obviously it's pretty easy to figure out what that pressure is, right? So let's work that out. The radiation pressure, and we're trying to relate that to the electric field, the radiation pressure, well, that's clearly the force on that surface over there divided by the area. How are we going to calculate that conveniently? Well, let's imagine a certain amount of time, so let's draw a little box. Okay? You can make this box any length you like, but let's the length of the box is equal to delta t, how long those photons have had to travel, times c. Okay, so imagine a certain amount of time, delta t, over which a set of photons, right, has got to the end of the box and fallen on the surface and bounced off it, or at least pressed on it. Let's forget about the factor 2 from the bouncing, right? So the total amount of momentum given to that surface on the end, right, the total amount in that time delta t. Okay, so I'm going to call it P subscript t. The momentum transferred is equal to the momentum density PA. Okay, just remind ourselves it's the density, and there's like an area at the end there. It's equal to the area times c delta t. Okay, right. So whatever the momentum density is, whatever the area is, that's it. But I can immediately see that that's just the volume, isn't it? That's the volume of that box. Yeah. So it looks like a little bit of jiggery-pokery, but it's all fine. And remember that the momentum transfer we define as being the force times delta t. It's the impulse, isn't it? So therefore we can simply write down that the force is equal to PA, the momentum density, times that area times c. Okay. Now since we know that pressure is another P, right, we're going to call that radiation pressure. I've got three symbols P, that's why I've given three subscripts. Okay. The density, I don't want to call it rho, I call it P, momentum density. So P is the momentum density, PT is the momentum transfer in a given, that's the total in a given time. But PR is the thing we really want, right? The radiation pressure, that's simply equal to the force divided by the area, and that's equal to the momentum density times C. Okay? So the algebra is trivial, it's just keep track of which thing you're talking about. Okay? And hey presto, radiation pressure is equal to the energy density U. Right? So whatever the energy density is, that is the radiation pressure. So we have three quantities. We have the radiation pressure, which is equal to the energy density in that EM wave, irrespective of the wavelength. And we can therefore relate it to the time average of the Poynting vector. Now we should really remark, of course, the energy density is a scalar quantity, and the Poynting vector is properly a vector quantity. I'm just going to put a modular sign around it to remind you that we're going to take the magnitude of it. Okay, divide that by C, and I can say the same thing about the individual electric and magnetic fields. 1 over mu naught C, okay, E cross B. Should really put some vector quantities there, and I take the size of that. So that really should be a vector quantity, shouldn't it? Okay. But you get the idea. It's the magnitude of the Poynting vector divided by C tells you the radiation pressure. Okay. Now you should take a look at that 1 over mu naught C. You can rewrite that. That's going to be a very important concept later. Very important constant later. You can clearly rewrite that in a variety of ways because C is equal to epsilon naught mu naught squared. Okay. Epsilon naught squared mu naught squared. Right. Sorry, 1 over root of that. Anyway, this will be important later. Now, some examples. Well, remember I just said that one thing we can be aware of when I have photons or electromagnetic waves travelling and striking a surface is they may indeed be reflected. Okay, and you already know that if I have a momentum going one way, that should be P gamma, and it's reflected, that photon is reflected, it comes back with the opposite momentum, and therefore obviously the radiation pressure in this case would be mod S over C, where that's the time average quantity, and I just multiply by 2. Okay? That's straightforward. Let's look at a couple of other examples. Again, it's good to start illustrating these things with real numbers. So let's try some real values. So let's think of we often see lasers in industrial and scientific contexts. Let's think about a CO2 pulse laser, which is a good example of a high power laser system where we expect there to be possibly some decent radiation pressure being exerted. And these days you can buy these things so that in one laser pulse there might be 100 joules of photons. Right? And in this particular case, remember that the radiation pressure shouldn't depend on the wavelength. These things laze in the infrared. And infrared means a wavelength of around about 10 microns, or 10 to minus 5 meters. Right? And once I said the pulse contains 100 joules in total, in order to work out what the radiation pressure is, we need to know how long that pulse lasts for. Let's pick a value. 10 nanoseconds is a typical number. And we can normally make these things so they give a beam radius. You can focus it into a spot, okay, which is of the order of a centimetre in size. So these are all kind of realistic numbers. And it's good to have a feel for how big those realistic numbers are. So if we were to imagine an actual laser pulse travelling along out of the laser, it would be C times 10 nanoseconds long, and when it strikes a surface it will do so with a radius of about 1 centimetre. Okay. And we're going to do an order of magnitude calculation. So we're going to work out that the energy density U is 100 joules and divided by pi r squared c tau, if you refer back to that previous formula. Therefore, it's easy then to work out what the pointing vector is. It's equal to c times u. Okay, and if u here is about 10, let's look at order of magnitude, 10 to the 5 joules per cubic meter. That's a lot, isn't it? Right. And if you multiply that by c, that's 3.2 times 10 to the 13, and a good way to write that unit part is watts per square meter. That makes sense, doesn't it? And then the radiation pressure, well, you simply go back again, divide by c again, and it's of the order of 10 to the 5. Rather than joules per meter cubed, it is newtons per meter squared. Right? That's heavy. So it's 10 to the 5 newtons per meter squared, but we remember that it's only a centimetre wide, that spot, so there's no force anywhere else. So that force over that 1 centimetre radius beam spot, okay, is about 32 newtons. In other words, 3 bags of sugar. Okay, right. So when that pulse is being fired, it exerts a force which is equivalent to throwing 3 bags of sugar at whatever it's hitting. So some of these experiments might be little foils, and they have a really big hit. And sometimes you blow the foil and you accelerate the foil up to relativistic velocity. So they use these kind of experiments to accelerate subatomic particles like electrons and protons and things like that. Right? Okay, so that's one end of the scale. Another end of the scale is, imagine I have the sun, maybe not in Manchester, right? You might have to wait for a few months now to see it again. But imagine it's up there and the light from the sun is spreading out over a very large amount of space. Okay? And you know what the luminosity of the sun is. That's the amount of energy being given out per unit time. It's spreading out as 1 over r squared. And there's lots of little bits and bobs floating around the solar system. So imagine a small particle, and that particle is going to see 2 principal forces. One of them is that radiation pressure, and the other one, of course, is gravity. So one's pushing it out, and the other's dragging it in. They're not necessarily orbiting particles, right? You can ignore the orbital bits. Okay. So what you do is you work out whether one is bigger than the other, and of course it will depend on the distance. Right. So what you do is, in the example sheet, you can work out for a given size of dust grain the ratio of the gravitational and radiation pressure forces. That's an interesting calculation. It tells you what kind of objects will remain gravitationally bound to the sun. Okay. Another example, if you have the same kind of solar radiation, that will impart momentum. You've heard of satellites with solar sails, right? You can pull out a solar sail and you can make a rocket out of that if it's large enough, and assuming there's no significant air resistance in space, which is reasonably true. Okay, so we do get radiation transport and pressure applied on solar sails, and the kind of typical scale sizes might be sort of football field, or the kind of rough area of that wall might be able to be enough that the momentum transfer can accelerate a small satellite or a small space probe. Okay, and another thing as well is within stars. Right, you have a variety of forces which are present within stars. You've obviously got the gravitational force, which is giving rise to the compression that gives rise to nuclear fusion, and you also have radiation pressure. And these two forces, this is a thermal pressure and a radiation pressure, they vary according to the mass of the star and its radius. Okay, because you'll have different ratios of these two quantities, and what you find is that large stars can be dominated by radiation pressure, but the sun isn't one of those. Okay, so there is a famous limit to that, which is called the Eddington limit, which is basically when you have so much luminosity from the star that it's no longer gravitationally bound, and that's an upper limit. That's one of the upper limits for the size of a star. Okay, which is a luminosity statement. Okay, 2:30. Right, that's section 1. Still enthused? We should get more enthusiastic now, because I think this next section is the bit we all came for. At least I did anyway. Okay, which is sources of radiation. Okay, so we've talked about what happens when they're carried. And you see that this plane wave statements and this derivation of the pointing vector are going to be very, very useful when we talk about whether or not something radiates. Okay, so let's go back to the very first lecture, many weeks ago now, well, 2 weeks ago now, okay? And we're going to talk about a charge. Here's my charge. Okay? So you know what charges look like, and we know that we can have a charge at some location r primed, as we define it. Let's zoom that out a bit. There we go. Okay. And we're going to observe its electric field at some distance over here. And the first thing we can say about this charge is we don't know which way round it is. So therefore it's an isotropic field, which means if we draw field lines, and remember those field lines are proportional to the amount of charge I have, they should be equal in density regardless of the orientation. And by applying Gauss's law, we can make the statement that the electric field varies as 1 over r squared. All right? You already know that. And we can observe a little more closely here. Imagine any two field lines, and you can see that the density of field lines, when you view the charge from any direction, when I observe those field lines and I double the distance, the density of the field lines falls by a factor of 4. That's another restatement of Gauss's law, isn't it? Right? And the other thing we can say is there's no magnetic field. Right? So what does that mean? Let's see if I can find my notes. There we go. Okay. Well, if there was radiation, then there would be a pointing vector. There would be energy being carried away in some part of the electromagnetic field. Okay, so let's look at the components of the electromagnetic field that are there. There's an electric field component which is 1 over r squared, and there's a magnetic field which is 0. But we know if there's electromagnetic radiation, firstly that these two components should be coupled together, right? And that the amount of energy, which we've said is proportional to S, that's the pointing vector. If there was energy being given out, then the magnitude of S should fall as 1 over r squared. It should be roughly proportional to 1 over 4 pi r squared, right? That's if energy is going to be emanating away from this stationary charge. So I postulate that there is energy being carried away from this stationary charge, and if that's the case, there should be a pointing vector S which goes as 1 over r squared. But I already know that means there should be an electric and magnetic field somewhere which each vary as 1 over r. Okay? Because when I multiply them together, I'll get a pointing vector which goes as 1 over r squared. Right? Because S is equal to E times B. Now, I can't see any of those components here, so therefore, there ain't no radiation. Okay? So a stationary charge does not have any components of the electric or magnetic fields which vary in the appropriate manner with distance from the charge, and therefore there is no radiation. That's our starting statement. The stationary charge does not radiate. Okay. So now what we should do is look at a moving charge, and I'm going to show that picture before. Let's show it one more time. Here's my stationary charge on the left, and you can see that the electric field is isotropic. That's on my uniform case that doesn't radiate. But now I look at the right-hand case. This is a charge which is in uniform motion, and when I look at that charge, and that charge is moving rapidly near the speed of light, I remark that the Lorentz transformation should compress the electric field lines. Now, I will apologise, there are 2 thetas. I'm going to try, I'll correct the notes here. I spotted that. It might be a little confusing. There are 2 thetas. The first thing I'm going to say is when I do the Lorentz transformation, hopefully you can believe that this is true. Because of that length contraction term, which goes as 1 over gamma, that means I expect that in the transverse direction, the direction transverse to the motion of the charge, which is that V there, the electric field line should be compressed. That's a Lorentz contraction statement. And that means the typical opening angle of the electric field, so a rapidly moving charge, the electric field becomes a pancake, which is moving along with the charge, and its opening angle is of the order of 1 over gamma. That's what I'm trying to say when I say the opening angle theta is the order of 1 over gamma. I'll change that in the online notes to another symbol, okay? Because I'm also going to show how you can explicitly calculate the electric field. Because, I mean, this isn't immediately obvious that these field lines also fall as 1 over r squared, right? Now, if you follow through the Lorentz transformation, you can calculate explicitly what the electric field is as a function of distance and also as a function of angle. And that's what this angle theta here is, okay? So that angle theta is the angle I'm calculating the electric field at for a given velocity, which is given by beta, which is v over c. Okay? So it's possible to show that this is the Lorentz transformation of the electric field, right? So clearly it varies. Now you see here it's insensitive to the orientation in the other direction, but it obviously depends on theta, right? So the electric field falls to 0 in the direction of motion, and it has a maximum transverse. That's what that sine squared term is. But then you look at the right-hand term, which shows you the magnitude, and you have the direction of the field in any particular orientation, and you have its magnitude, and hey presto, the electric field falls as 1 over r squared explicitly. Okay? Now, you can maybe convince yourself, without looking at this equation, that must be true, because if I take any two field lines, and I follow them outwards, and I double the distance along some path away from the charge, again, those field lines drop in density by a factor of 4 whenever I double the distance away from the charge. Okay? So whether or not you accept it via this explicit derivation or pictorially, hopefully you can convince yourself that the electric field in any particular observation direction still falls as 1 over r squared for a moving charge. And again, this is a uniformly moving charge. Right? So a uniformly moving charge has an electric field which falls as 1 over r squared. It also has a magnetic field now, doesn't it? Right? And you can show that the magnetic field also falls as 1 over r squared. But again, the electric field has no component. I'm not quite sure what to say. Let's say so. It is not true, okay, that the electric field has a 1 over r component. And straight away that tells you if there is no 1 over r component, then there can be no electromagnetic radiation. There can be no part of that electromagnetic field which can be thought of as being something propagating away. That propagation away is carrying away energy. The energy is given by the pointing vector, and the pointing vector must have this E term in it, and we know that B is proportional to E. Okay, so therefore there's no radiation from that either. All right. So there we are. So both of these cases don't work for radiation. So therefore we must have an acceleration. So we'll get to that in a bit, and we're going to show explicitly what that radiation field looks like. But before we do that, we should also look at another phenomenon, because that will help us explain how to calculate that electric field. And this is the concept of the retarded potential. So I've just been through section 2.1, which is in the handwritten notes. Now let's look at section 2.2, because there's another important statement about radiation, and that's to do with the concept of the retarded potential. Okay, so we're going to talk about retarded potentials. Okay. Now, remember we had our scalar and vector potentials, which we derived, and we were able to show that the scalar potential, capital Phi, satisfies a wave equation, but there was an additional part. This is an inhomogeneous equation. There is a source term to do with the charge density. Okay? So this says that the scalar potential Phi is brought about by virtue of there being a charge or a charge distribution. Similarly, there was a vector potential, and that vector potential is brought about by there being a current. And of course, this second equation is really three equations in one, because the current in the x direction defines the vector potential in the x direction, and so on for y and z. So these are wave equations, okay, with the so-called source terms rho, and j, the charges and currents. Okay, so far so good. Now, let's first revisit our static case, the case of a stationary charge. d by dt equals 0, in other words. Okay, so any terms d by dt disappear. So in that situation, we obtain del squared phi is simply equal to minus rho over epsilon naught, and therefore it has a solution phi, the potential at any given location of observation r. This is a reminder, right, because we did this before, 1 over 4 pi epsilon naught, and I look at integrating my charge distribution over some volume, and I count up all my little charges over that volume, and I look at how far away they are from where I am looking, which is vector r. Okay? So I can think of that as being here's my volume, okay, and that's one piece of the charge distribution. Remember that was dq equals rho dv primed. So that was r primed given with respect to some origin. Okay, and I'm observing over here, that's r, and that's r minus r primed. Okay, so we have a superposition of little pieces of charge, as so. Okay, should be a magnitude of r minus r primed. Okay, so we've seen that before. And obviously the vector potential looks just the same. Mu naught over 4 pi, integrate over the volume, okay, dv primed, j r primed over r minus r primed. Okay. Now we have a time-dependent case. So in our time-dependent case, these charges are no longer still, which is annoying. So we can't simply integrate where those charges are, because by the time we observe over here, by the time our knowledge of where the charge is has propagated to the observation location, the charge might have moved. Right? So there's already a difference between when we are observing and when the charge density is calculated. And clearly all these different places in the volume have different distances to the point of observation, any given point of observation. So I need to take account of the fact that I need to, in order to work out the total potential, I need to say, add up, so let's add another charge, okay, so that one there. I need to take account of the difference in propagation times between those two source charges, right? So I might call them now, this is R1, and this might be R2, okay? Have I got that right? R2 primed, that should be R1 there, okay? That one, this one goes with that one, and this one, yeah, let's make that R1, make that R2, right? So this is R minus R2 primed, okay? So the important thing here is that the potential that I see here depends, at any given time, depends on what the charge density at this location was at some earlier time, at some retarded time. Okay, that's fact number one. Fact number two is if these two distances are different, I can't just use some universal time. What I have to do is I have to, for each piece of charge, I need to integrate it, taking account of that difference in time. That's that propagation time, assuming that my knowledge of the electric field is moving at the velocity of light, c. Right? So I need to define first a retarded time tau. So tau is, so I imagine that I have some charge density at some point, which may vary with some variable t, but when observed at some distance, which is given by r minus r prime, so this is some global t, and this is r prime where that piece of charge is. The retarded time that goes with that little piece of charge must be defined as like so. Okay, it's t minus r hat over c. Okay, so this is the retarded time for that little piece of charge. Right? Okay, and that's simply expressing the idea that it takes a certain amount of time for information to get from r hat to r. Okay. So really we need to rewrite our potentials. So rather than our ordinary potentials that we wrote above, we need to rewrite them and put that tau in. Okay, so let's do that explicitly. So these ones are static ones. They don't have any time in them yet, but really we want to have retarded potentials. So let's write those down. So now my potentials will vary both with the observation location and with some global time t. I still have the same prefactor for that potential. And I'm still integrating over some charge distribution. Right, so I'll put the dv primed on the right. So I need to write down carefully what rho is. Rho is the charge density at some location r primed, but calculated at a time which is earlier than the time I'm observing it at, and it's earlier by the distance to the location where I'm calculating the potential. Okay. Still the same distance, so you can see I'm calculating the same volume elements, and they all have the same distances. I'm just saying to myself the potential might be leaving or entering that little piece of volume. And the same thing is true for the vector potential. It's just the same. Different prefactor because it's currents rather than charges. Same volumes, okay, but now I'm looking at the current density, which again may vary with time, and I need to correct for the fact that when I'm observing it at some distant location, I need to account for that propagation delay. That's the retardation. Okay. Now, it is fiddly to show that these satisfy the wave equations, but they do. And Jackson, we said, be wary when you go in it, but Jackson chapter 6, okay, will show you how that's done. Okay. Also, so it satisfies the wave equations, and also it satisfies the Lorentz gauge. So everything's still okay from that point of view. Okay. So now we're in a position to look at what the radiation field looks like. So remember our statement, so we've said it a couple of times now. We must have an accelerated charge. So in a couple more minutes, I'll just show you what that looks like, and then we'll look at it in a bit more detail. Okay? So here is my example situation. Now there are a variety of ways of moving from our statement that we need to, in order to work out, so here we have some observation direction, and we know that there must be an acceleration of a charge in order to get a radiation field created. We can do it mathematically from the retarded potentials, and you can follow through that derivation. I'm going to show you a pictorial derivation which gives you everything without having to do the retarded potentials directly. But what we have to accept is that when I'm calculating the electric field at some observation location over here, okay, I can show it with the retarded potentials directly. So what am I showing here? This is a kind of, I guess it's a Gedanken experiment, you might call it, right? But this is an example which we can then generalize to look at any form of acceleration. So I posit that I have a stationary charge, and I'm going to, for convenience, define that it's at some time equals 0. It starts with no velocity, u, and it's going to eventually be moving up this page. Okay. I then say it moves from P to Q, and during that short time, delta t, it undergoes an acceleration. Right? So it undergoes an acceleration, but after it finishes that acceleration, it is still moving at some velocity which is much less than the speed of light. Okay? What does that mean? It's gone from being stationary to moving with some uniform but small velocity. So for all times greater than delta t, it is now moving uniformly. So therefore, close to that charge, which is now moving slowly upwards here, it it exerts, or it creates an electric field around it which is moving along with it. And because the velocity is much less than the speed of light, that electric field pattern is still basically isotropic. It's not compressed by any Lorentz transformation. Okay? So this simpler picture we can obviously extend to other situations later. So we see that we have a small acceleration term. We think, well, so what? Well, first thing to think about is, what does our observer far away see? Our observer far away, in the initial situation before the acceleration occurs, they see what you expect them to see. They see an electric field which points backwards to where P is. Okay? That's what I'm trying to show with that dotted line. Okay? So the observer's over here, and the charge is over here, for some distance away, and it starts to accelerate, and it accelerates for a short time, but of course the observer doesn't know that yet. They need to wait long enough to be able to see the new uniformly moving charge, which still has an isotropic field pattern around it, but it's now moving. And I have to obviously wait a time, that's my retarded time, I have to wait a time t equals r over c in order to see the new electric field. Okay? But I haven't got there yet. So this little boundary here, that's showing the situation at some intermediate time, before enough time has elapsed such that the new q location, or the new q motion of the charge, can be seen by the distant observer. Right? So close to the charge, I have the new electric field, and far away, I have the old electric field. And remember what we said before, that electric field lines have to start and end on charges. So there was a little bit of a cheat here, because there are little sharp corners there. But I'm going to say the electric field line is still somewhat continuous, right? There are no extra field lines appearing, and I'm going to make myself happy later by saying, well, this is meant to be an abrupt acceleration. I can imagine some sinusoidal acceleration, and then this shape will be somehow smoothed off. We'll accept that's mathematically okay. But what can we see? We can see that if all the field lines must remain continuous, there's the same number of them, there clearly has to be some kink in the electric field, right? And notice the direction of the kink of the electric field. The kink of the electric field is more or less transverse to this radial electric field. Remember, that radial electric field falls as 1 over r squared. Okay? So that kink in the electric field is propagating away from the charge. So obviously, that's the radiation. Okay? So on Friday, we'll work out what that does and how strong it is. Okay? So that's what we're going to do then.